talk about secondary ion mass spectrometry, which is called SIMS. SIMS is an analytical technique based on the measurement of the mass of ions ejected from a solid surface after the surface has been bombarded with high-energy primary ions. As we can see, based on the diagram, we are looking at the primary ions going in, and then we look at the ions that came out, we call secondary ions. Well, the nice things about SIMS is because it measures mass of the ions that are coming out. We allows to examine things like isotope. SIMS is a surface analysis technique used to characterize the surface and subsurface region of materials, and based on the mass over electron ratio, measurement of ejected particles under ion bombardment. So this is a block diagram of SIMS technique. Most of these instruments are characterized by a surface region in which the intensity, energy, and orientation of the primary beam are controlled. Ions generated by this process form the secondary beam and are subsequently transmitted within a continuous high vacuum environment to a mass spectrometer. Most SIMS instruments used for elemental and isotope analysis function by accelerating ions produced in the source along a potential gradient, typically 10 kV, and then transferring these ions into the mass spectrometer. Details of the configuration of the mass spectrometer vary from one application to another, but all utilize both magnetic and electrostatic analyzers, commonly referred to as sectors. The advantage of this configuration is that the electrostatic filter reduces the energy range of the secondary ions so that they can be separated into independent ion beams by passing them through a magnetic field. So, the secondary ions are formed at the sample surface by the bombardment of the primary beam. These secondary ions are immediately removed by an extraction or immersion lens. In the chemical system, the sample is held at high potential and the first member of the extraction lenses is at ground potential. Depending upon the polarity of the sample, positive or negative secondary ions may be extracted. The polarity of the secondary ions is user-selected and is independent of the primary beam polarity. In order to obtain a constant secondary ion beam current, the potential difference between the sample and the extraction lens must be kept constant. I will explain for the secondary ions transfer. After the secondary ions has been extracted from the sample surface by the immersion lens, they are transferred by a second electrostatic lens into the mass spectrometer. The purpose of this transfer lens is to form a real magnified image of the sample surface at the position of the field aperture and to focus the secondary ion beam into the entrance slit of the spectrometer. At the same position as the entrance slit is the contrast aperture. Smaller contrast aperture intercepts ions with off-axis components, resulting in greater spatial resolution but reduced ions intensities. The immersion lens and the transfer lens together form the chemical ion microscope, which enable an image to be viewed by an appropriate detector at the position of the field aperture. When the primary beam raster is large, the secondary ion beam can at times be off-axis. This results in aberrations at the entrance slit at the spectrometer and prevents clean separation of the different masses. The structure of the SIMS is the secondary ion detector, which include the electron multiplier, Faraday curve, and the resistive encoder. The electron multiplier is the most sensitive detector. If protected from stray ions, naturals, and cosmic rays, then the background count rate is normally less than 0.01 counts per second. However, the multiplier must also be protected from intense ion beams, as this can rapidly lead to its destruction. A Faraday curve detector can detect count rates from 5 times 10 to the power of -4 per second upwards. Unlike the electron multiplier, it does not discriminate between the type of ion or its energy. It is simple and cheap, but its response time is low. The Faraday curve detector consists of a hollow conducting electrode connected to ground via a high resistance. And the last one, the resistive anode encoder, is a position-sensitive detector. It is used to digitally record ion image. The background count rate is high but constant over a period of time, and the maximum count rates must be less than 4 times 10 to the power of 4 count per second, because it uses a microchannel plate for the ion to electron conversion. The detector discriminates between species.
First of all, ion gun consists of three types, which are gaseous elements that are usually generated with dual plasmatron. This type of ion gun is easy to operate and generates roughly focused but high current of ion beams. Small amount of noble gas such as argon and neon become ionized by interacting with free electron and forming plasma. A second source type is the cesium surface ionization source that will generate cesium primary ions. Then cesium atoms will vaporize through a porous tungsten plug and are ionized during evaporation. Fine focus or high current can be obtained depending on the design of ion gun. A third source type is the liquid metal ion gun, which known as LMIG, that operates with metals or metallic alloys which are liquid at room temperature or slightly above. The liquid metal covers a tungsten tip and emits ion under influence of an intense electric field. The LMIG provides a tightly focused ion beam which lower than 50 nanometer with moderate intensity and is additionally able to generate short pulse ion beams. Therefore, it is suitable for static mode of secondary ion mass spectroscopy. Mass analyzer, also known as one of the basic instrumentation in secondary ion mass spectroscopy. There are generally three basic analyzers available, such as sector field mass spectrometer that use a combination of an electrostatic analyzer and a magnetic analyzer to separate the secondary ions by their mass to charge ratio. Whereas for quadruple mass analyzer that will separate the mass by resonant electric field, which allow only the selected mass to pass through. Last but not least is time of flight mass analyzer that will separate the ions in a field-free drift path according to their velocity. Since all ions possess the same kinetic energy, thus time of flight will vary according to mass. It requires pulse secondary ion generation using either a pulse primary ion gun or pulse secondary ion extraction. There are many kinds of ion detectors that involve in secondary ion mass spectroscopy. For example, electron multipliers that known as a serial connection of discrete metal plates called diodes that amplifies a current of ions by a factor of 10 to the power of 8 into a measurable current of electrons. For Faraday curve, it has ability to measure higher ion currents where the electron multiplier struggles, since it consists of a hollow conducting electrode connected to ground through a high resistance. For photomultiplier conversion diode, the ions initially strike a diode which gives a result in electron emission. For array detectors, it can cover a broad range of detector types and systems, but can be generally broken down into two categories: either detectors that can measure many ions of different mass to charge ratio values simultaneously, or those types of detectors that are position sensitive. How does SIMS work? SIMS begin with the ions generated by this process from the secondary beam and are subsequently transmitted within a continuous high vacuum environment to a mass spectrometer. Most SIMS instruments used for elemental and isotopic analysis function by accelerating ions produced in the source along a potential gradient, typically 10 kV, and then transferring these ions into the mass spectrometer. Details of the configuration of the mass spectrometer vary from one application to another, but all utilize both magnetic and electrostatic analyzer, commonly referred to as sectors. If the electrostatic analyzer sector precedes the magnetic sector, the design is referred to as forward geometry. The advantage of this configuration is that the electrostatic filter reduces the energy range of the secondary ions so that they can be separated into independent ion beams by passing them through a magnetic field. In this configuration, multiple ion beams can be measured simultaneously. There are two modes of secondary ion mass spectroscopy. First is static SIMS. This mode uses a much lower energy primary ion beam, usually gallium or cesium. This technique is typically used for analysis of atomic monolayers on material surface to obtain information about molecular species on material surface, such as organic compounds. For dynamic SIMS, the primary ion beam exceeds the static limit and produces a high yield of secondary ions. This technique is used for bulk analysis of elements and isotopes, and is particularly well suited for analysis of isotopes and trace elements in minerals. There is advantages and limitation of secondary ion mass spectroscopy. For advantage, volume of material sputtered is small. Using a high energy and a high primary beam densities, such as dynamic mode, a volume of 100 to 1000 micrometer cubic is analyzed. Next is high sensitivity, means that samples with low concentration levels down to ppb levels can be analyzed with secondary ion mass spectroscopy. And also little or no sample preparation may be needed. For example, a typical uranium lead only consumes a few cubic micrometers of sample. For limitation secondary ion mass spectroscopy, the material spotted from the sample surface consists not only of monoatomic ion, but molecular species that can dominate this spectrum. Second is no quantitative models currently exist, since both atomic and molecular species are produced during sputtering of the sample, cause not all elements in all substrates can be analyzed quantitatively. Last but not least is samples must be compatible with ultra-high vacuum.